Hi, everybody. It's Professor Mitchell. Today we're starting Chapter 3, which is describing, exploring, and comparing data. So the first section is 3-1, measures of center. This is where we're going to be talking about mean, median, mode, and all that good stuff. All right, which is, I guess, sort of my way of saying what you see here. All right. Okay, so in general, when we talk about the mean, the median, the mode, we're talking about measures of center. Any value at the center or middle of a data set. That is a super loose definition, kind of vague. Okay, but for each one of those things, the mean, the median, the mode, we will make it a lot more specific. Okay, so starting with the mean. This is what is commonly called the average, although they're going to say something about the term average here in a little bit. The mean is when you add up all the numbers and divide by how many there are. So you've probably all done that before. I think I just did it with my pre-algebra class last week. Okay. All right. So some properties of the mean. Sample means drawn from the same population tend to vary less than other measures of center. I think that's something we're going to be talking about later in the semester. The mean of a data set uses every data value, right? You add up every single value and then divide by how many there are. One disadvantage of the mean, and I think we've talked about this before sort of unofficially, is that an outlier, which is an extreme value, can change the value of the mean substantially. Think about that exam where, you know, nobody does well except for that one person gets a 99. All right, so that 99, especially if it's a small class, will bring the mean up a little bit. Okay, so when you have extreme values, the mean is not the best measure of center. So any sort of measure like that where a few extreme values change the value of it, let's back that up for a second. If a few extreme values don't change that measure, then the measure is called resistant. So the mean is not resistant because one or two extreme values will either drag it up or drag it down. Okay. All right. So here's that again. A statistic is resistant if the presence of extreme values or outliers does not cause it to change very much. All right. So here we get into our fancy notation for doing statistics. So you're going to see quite a bit of this for different things. When you see this sort of sideways looking letter M, that stands for the sum. That stands for sum. Okay, add them all up. When you see an X, that's the variable usually used to express the individual data values. Okay. And then N is always used to represent the number of data values in a sample. Okay, if we talk about the number of data values in a population, often that's a capital N for number in a population. Ah, there it is. Okay, I forgot that they said that in here. All right. So to find the mean, and this is the mean of a sample, you add up all the X's, add up all the values in the sample, and then divide by how many there are. Okay, that's what this notation means. The sigma means add. So this means add up all the X's and then divide by how many there are. So if you're finding the mean of a sample, that is denoted X bar for the mean of a sample. The mean of a population is denoted mu, MU. So this is sort of a tradition in statistics. We use Greek letters for parameters, which are characteristics of a population. and you use regular letters for characteristics of a sample. Okay? So, but it's the same idea, right? You add up all the x's and then divide by how many there are. The only difference is lowercase n for sample, uppercase N for population. All right, so here is an example of finding the mean. Data set 32, airport data speeds in Appendix B. So this is referring to the textbook. We don't need this whole data set. They're just asking me to use the first 5 values. In general, I'm pretty sure these data sets are available online. And I don't think you even have to go through Canvas or my math lab or anything. I think they sit on a website somewhere. I guess we'll find out when we get to a point where we need one. All right. But in the meantime, this data set includes measures of data speeds of smartphones from 4 different carriers. And they want us to find the mean of the first 5 data speeds for Verizon, which you see here, these 5 values in megabits per second. Okay. So that's pretty easy. They're asking me to find the mean, so I'm just going to add those all together and divide by 5, right? And there it is. So yes, and I remember we're going to be doing something with these same 5 values in the next section. So I actually had occasion to find this mean again in section 3.2, and that number definitely looks familiar. So, but I did not check their work here, right? But I know that's right. Okay. So you add them all together. You might want to check, get out your calculator. Just make sure you agree those add up to 153.7. Divide by 5, you get 30.74 megabits per second is the mean of those 5 values. Okay, so here's the thing I was referring to before. So they're telling me to never use the term average when referring to any measure of center. I think some people do use average for mean. I don't think I've ever heard it used for median or mode. They're saying here that it is sometimes used for those. So to avoid confusion, we will all, including me, try to break the habit of using the term average, okay? You may catch me once or twice using the word average. I apologize in advance, all right? It's a hard habit to break. If you do catch me using the word average, I'm almost certainly talking about the mean, okay? But I'm gonna try not to use it, okay? All right, the term average is not used by statisticians, not used by the statistics community or professional journals. So they really have a thing against the term average. Okay, that brings us to the median. So the median is less familiar to a lot of people. I do hear it used sometimes in the news, and every time I hear it used in the news or in a podcast or something, they always explain what it means. They define it, okay? Because I guess a lot of people don't know what it is. The median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. So as long as you have them either in increasing or decreasing order, the median is the middle number, okay? Now that immediately brings up a question that we're going to talk about here in just a minute. Okay, the median is a resistant measure of center because if I, imagine an exam where, the second highest score is an 82 and the highest score is a 90. If I change that 90 to 100, it's not going to change the value of the median. Okay, median does not change by large amounts when we include just a few extreme values. So that makes it a resistant measure of center, and that's why I like to use it when I need a measure of center for exam scores, because I don't really want extreme values to affect it. The median does not directly use every data value. Okay, so again, if you change the largest value to a much larger value, the median doesn't change. Okay, it does not directly use every data value. Now, if you change a whole bunch of them, it will change. Okay. But it really just goes by, you know, what's the middle number when you put them in order. Okay. This notation is not as universal as X bar for sample mean. The median of a sample is sometimes denoted by X tilde, or, and I'm not sure I've ever seen either these other two at all. They have this boldface capital M or MED. All right, I sort of like X tilde, but I don't think I even use that all that much. I don't seem to use any notation for the median all that much. All right. Okay, so to find the median, first sort the values, arrange them in order, and then follow one of these two procedures. If the number of data values is odd, then there will be a middle. So imagine there are 5 numbers. The median would be value number 3, the one right in the middle, right? 1, 2, 3, 4, 5, right in the middle. However, if the number of values is even, then there will not be one in the middle, right? Imagine 1, 2, 3, 4. The middle would be somewhere between 2 and 3. And actually, that's exactly how we do it. So if the number of data values is even, then the median is found by computing the mean of the 2 middle values. Okay, the mean of the 2 middle values. So again, if you had 4, you would find the average of the second and the third. Okay, so here's an example of finding the median using these same 5 values that we used in the mean example. Now they want me to find the median. So let's see, the mean was 30.74, I think. So we'll see, how does that compare to the median? Well, when you put them in order, they come out looking like that. Clearly, the one in the middle is the 23.1. So the median is 23.1. Notice that that is much, much smaller than the 30.74. That was the mean. And I think I can, well, explain that by saying that this 55.6 is a pretty large value relatively to the others, right? Jumps way up to that 55.6. So that 55.6 is going to pull the mean up, but it's not going to really affect the median. Okay, so the median is smaller than the mean. Okay, so I'm going to ask you now, if you're watching the video, to pause the video and try to do this one. So now there are 6. So see if you can remember what they said about using when you have an even number of data values. All right. So you put these values in order. I think the new value was the 24.5, so that goes right there. This is one of those cases where there are 2 in the middle. So you take those 2 in the middle, the 23.1 and the 24.5, and you find the mean of those. Okay. Notice they're doing something here, I think, that they have not mentioned yet, which is that all of these values end in 1 decimal place, right? So what they're getting ready to tell you pretty soon is that when you find the mean or the median, you should include 1 more decimal place than you see in the original data. So that's why they have this 0 on the end. Okay? All of my data has 1 decimal place. So when I report the median, I'm going to report it to 2 decimal places. Okay? That just sort of happened automatically when we did the mean, right? Because the mean came out to 30.74. All right. Here's my shortcut. This is the slide I added. I picked this up from another book 100 years ago. So especially when you're working with a large set of data, it may be helpful to think of the median. Just think of it this way. This is not an exact thing. It's just a shortcut. Think of the median as being the n plus 1 over 2 ist. In other words, think of the median as being in that position n plus 1 divided by 2, in the list of n values when the values are arranged in order. So depending on whether you have an odd or an even number of values, that will come out to be either a whole number or a number ending in 0.5. If it comes out to a whole number like 20, that just means the median is the 20th value in the set. But if it comes out to a 0.5, like a 27.5, you have to remember that means that the median is the mean of the 27th and 28th values. Okay, that brings us to the mode. So the mode of a data set is simply the value or values that occur with the greatest frequency. Okay, the most commonly occurring values. Okay, probably to me the number one most important thing about the mode is that it can be used for qualitative data, and it's just about the only measure of center that can be used with qualitative data. All right, you know, if I ask everybody what's your favorite flavor of ice cream, I'm going to report the mode when I, you know, say what was the winner of the favorite ice cream contest. And then even if there are, I'm kind of getting a little ahead of myself, but, well, you'll see an example of this. There are certain numbers where it just doesn't make sense to add them up and divide by how many there are, and it doesn't even make that much sense to put them in order. Okay. All right, so a data set can have no mode, or one mode, or multiple modes. And different books have different feelings about how to report the mode, especially if you have multiple. Okay. All right. When two data values occur with the same greatest frequency, and that happens pretty often, each one is a mode, and the data set is called bimodal, right? Bi is in two. Okay. Where, on the other hand, some books, you know, will say something a little different about this situation. When you have more than two data values that occur with the same frequency, your book says that the data set is multimodal. Each one is a mode. I pretty frequently teach out of one book that says in that case, we just don't report the mode because it's not all that informative. Okay, it doesn't tell you all that much. Okay, and then the other thing that can happen is that every single value occurs one time. And in that case, you just say there's no mode. Okay, so we're kind of giving away this answer right away. Sorry, I just didn't have time to, you know, fix this so that the circles wouldn't appear right away. But I think it's easy enough. Find the mode of these sprint data speeds. So there are 7 of them there, and there's one that occurs 3 times. Right? Oh, and there's one that occurs 2 times. But the winner, as far as mode goes, is the 0.3. So that would be the mode. Okay. All right. Here are a couple of other examples of mode. So this data set, 0.3, 0.3, 0.6, 4.0, 4.0 has 2 modes, 0.3 and 4.0. And this set, 0.3, 1.1, 2.4, 4.0, and 5.0, that has no mode because none of the values are repeated. Okay, that brings us to the mid-range. So the mid-range is, well, let's just talk about what it is. Measure of center that is the value midway between the maximum and minimum values in the original data set. All right, so it's kind of a shortcut lazy mean, sort of. Instead of using every single value and dividing by how many there are, you're just using the largest and the smallest value. Okay. All right, the maximum plus the minimum divided by 2. That's called the mid-range. The mid-range is not resistant because it uses only the maximum and minimum values. So if you change either the maximum or the minimum value, the mid-range is going to change a lot. So that makes it not resistant. The mid-range is not used all that much, but some advantages of the mid-range: it's very easy to calculate, helps reinforce the important point that there are several different ways to define the center of a data set, and the value of the mid-range is sometimes used incorrectly for the median. So confusion can be reduced by clearly defining the mid-range along with the median. All right, quick example with the mid-range. So find the mid-range of those same, I think they're the same 5 values that we keep using in a bunch of examples. All right, so when you, you just have to identify the maximum and the minimum. The maximum is 55.6, the minimum is 14.1. The mid-range comes out to 34.85 megabits per second, I think it was. Okay. Okay, round off rules. For the mean, median, and mid-range, carry 1 more decimal place than is present in the original set of values. So in the example that keeps coming up over and over with the 5 data speeds, those were all rounded to 1 decimal place, and that's why they reported the mean, the median, and the mid-range to 2 decimal places. And that especially stuck out when they did the median, because I think the median came out to be 23.8 or something like that, but they called it 23.80 because they were reporting 2 decimal places. Okay, however, for the mode, leave the value as is without rounding, because values of the mode are the same as some of the original data values. Okay, so mean, median, mid-range, use 1 more decimal place. Mode, leave it alone. Okay. We can always calculate measures of center from a sample of numbers, but we should always think about whether or not it makes sense to do that. Okay? And we should also think about the sampling method used to collect the data. So I think coming up here, you're about to see a couple of examples where it wouldn't make any sense to find the mean, for example. All right, zip codes. Zip codes are a good example of well, they're really qualitative data, because yes, they're numbers, but they don't really make any sense as numbers. They don't measure anything or count anything. So you would never think about adding a bunch of zip codes together and dividing by 5. Right? That just wouldn't make any sense. All right. This makes a little bit more sense, but still not complete sense. Ranks of selected national universities are 2, 3, 7, 10, and 14. So those ranks do reflect an ordering, but again, they don't measure or count anything. So I would never think about especially using the mean for those. Okay. All right, mean from a frequency distribution. So this will make a little bit more sense when you see the example, but to find the mean from a frequency distribution, you multiply each frequency by the class midpoint and then add all those products together. And then divide by how many there are. And the easiest way to get how many there are is to just add up all the frequencies. Now notice the little note that they put here. The result of finding the mean from a frequency distribution is an approximation, because if they hand me a frequency distribution, then I really don't have the set of original data. I just know that, for example, there's 12 that are between 10 and 19. And I know there's 18 values between 20 and 29, but I don't know what the original data values are. So this is going to be an approximation. Okay, so here's an example of finding the mean from a frequency distribution. The tables shown here are the same as the frequency table of 2-2 from chapter 2. So you've seen this example before. This is for the waiting times in the McDonald's drive-thru, right? Okay, so I've shown my work on the next few slides. The first thing I'm going to do is find the class midpoint for each one of those classes. And remember, the way that you do that is you add the lower and upper class limits and divide by 2. In other words, just find the mean of the lower and upper class limits. So when you do 75 plus 124 and then divide by 2, that's how you get the 99.5. When you do 125 plus 124, sorry, 125 plus 174 and then divide by 2, you get 149.5. Okay. So these are my frequencies. Notice they add up to 50. So when I go to find this mean, I'm going to be dividing by 50. Here are the class midpoints. So now the next thing I'm going to do is I'm going to multiply each frequency by its class midpoint. And that is how you come up with this. 11 times 99.5 is 1094.5. 24 times 149.5 is 3,588. 10 times 199.5 is 1,995. You add those together, you get 8,025. So the next thing I'm going to do is divide that 8,025 by 50. Okay. So notice that when we're working with data summarized in a frequency distribution, we make calculations possible by pretending that all sample values in each class are equal to the class midpoint. Okay. So hopefully it's a pretty good approximation, because you're going to have some values in the low end of the class, some values in the high end of the class. So by just using the class midpoint for all of them, hopefully that gives you a pretty decent approximation. Okay, so your sample mean is going to be add up each frequency times midpoint, and that gives you the 8,025 that you saw on the last slide, and then divide by 50, and to one decimal place that comes out to 160.5. So my approximation, and I just noticed a typo here, this X here should be an X bar. I'm just noticing that for the first time here. I think I can fix that. There you go. All right. 160.5 is, 160.5 is an approximation because it's just using midpoints. Okay. Might be interesting to see how does that compare. We have this original data set. So if you ever have some time to kill and you're really, really bored, add up those 50 numbers and then divide by 50 and see what that comes out to. That would be a great thing to use Excel for. Okay. Would not want to do that by hand. All right. Okay, very similar concept is weighted mean. When different data values are assigned different weights, you can calculate a weighted mean. So my favorite example of a weighted mean is grade point average. In her first semester of college, a student of the author of your textbook took 5 courses. Her final grades, along with the number of credits or units for each course, were A in a 3-unit course, A in a 4-unit course, B in a 3-unit course, C in a 3-unit course, and unfortunately an F in a 1-unit course. The grading system assigns quality points to letter grades as follows. A is 4, B is 3, C is 2, D is 1, F is 0. Okay. So we have enough information here to calculate this student's grade point average. So the way that that works is use the numbers of credits as weights and replace the letter grades of A, B, C, and F with the quality points 4, 4, 3, 2, 0. Okay. And I like to do it in the form of a table. It didn't come like that when I first pulled this up. I like to do it like this. So here are the grades listed along with the quality points. Here is the weight of each grade. And then what I'm going to do is multiply each grade by its weight. So 4 times 3 is 12. 4 times 4 is 16. 3 times 3 is 9. 2 times 3 is 6. 0 times 1 is 0. So over here you have this formula that's very similar to your mean from a frequency distribution formula. Add up each weight times X. Add those all together. They add up to 43. It's really easy to do that in the table when you do it in the form of a table. And this student was taking a total of 14 units. When you divide 43 by 14, it comes out to about 3.07. Grade point average, so normally using their rounding advice, you would round that to 3.1, except as you know, grade point averages are usually rounded to 2 decimal places. All right? So we'll go with that. Okay, so again, the result is a first semester grade point average of 3.07, and if you went with their round off rule, you would round that to 3.1, but usually grade point averages are rounded to 2 decimal places. And that takes care of section 3.1.